Welcome to Drone Systems and Control course. In this lecture we are going to talk about the emerging technology of UAV swarm, right. We'll talk about why swarm is needed by looking at some of the well known problem like defense games, forest fire setting, search and rescue mission or payload transfers, right. And then we define what are the general problems in swarm technology. Then we look at two important problem, one on the perimeter defense, basically when anti-drone kind of a solution, right. I want to protect my government building or a specific area, right. I have a drones which is monitoring the perimeter. If I see an enemy drone entering into my perimeter, I want to neutralize. Nobody knows when the enemy drone is going to enter, right. If you look at, it can enter in anywhere in the perimeter. So it's a spatially they can be anywhere, temporally they can be anywhere. So it becomes a spatial temporal problem. We'll talk about it. That's why swarm is needed. Same goes to forest fire, right. When you have a forest fire kind of a problem, you need a distributed swarm to handle it, because forest fire will have multiple clusters of fires. Certain fires can be handled by a single drone, certain fires require more than one to act simultaneously. The number of people required is based on the size of the fire. Once the size decreases, having more person is not going to help, right. So we will understand how distributed swarm is going to play an important role there. Okay. Now let's look at a typical payload transfer kind of a problem. I am designing a drone which can carry a specific payload, but suddenly there is a payload which is much more than a required sizes are there. Then designing a new drone for that payload is again going to increase the complexity, because the size of the system will increase. Now there is a challenge. If you look at typical logistic transfer, right, the size of the payload is not going to be constant all the time. You may have to decide, I am going to make a drone which is capable of carrying a 10 kg. I will try to pack everything in 10 kg. Suddenly there is a requirement comes, I want to carry 40 kg. And that requirement is not going to be quite frequent. Most of my requirements are going to be 10 kg. Then is it possible for multiple drones to come together and carry the payload from point A to point B, right. That is a cooperative payload transfer problem. Now here the challenge is the drones, let us say I am putting four rods to which the drone need to be connected, right. The four drones have to come together, lock on to that particular mechanical connectivity, right. How the connectivity, how it can help is a problem by itself, right. How to do the gimbal and all this, we need to look at it. Now that is not alone is a solution. Let us say if they are just carrying from A to B, they all have to cooperatively track the trajectory such that they can go from point A to point B, right. If one drone goes slightly higher, it will induce a force on the others, right. They have to maintain the position so that they can safely transport. But then what will happen, think about it, what will happen if you have obstacle on the way, right. They have all come together, attach, carry the payload from point A to point B, and the carrying is also very challenging problem, because if they get into a trajectory where they need to accelerate, right, that will also affect the load on others. And if the disturbance comes into picture, suddenly a pole or a rod comes into picture, they need to know how to avoid the pole, right. They cooperatively they have to navigate. That is an interesting problem where cooperation among them is needed, right. Not just that, the architecture should be the same. You can't have a separate control architecture for swarm based operation. You can't have separate architecture for individual payload delivery. Not possible, because you have to have a unified architecture so that they can work together, right. So that is a challenging problem altogether. Now when you have obstacle comes into picture, you have obstacle where you can yaw and move, you have obstacle which is moving up and down, then you may have to accelerate or decelerate to avoid the obstacle, right. That is another challenging problem, right. Sensing the obstacle and then communicate among other UAVs is also important factor. I am just giving a scenario like when you have 8, the trajectory is more of 8 shape, you need a constant acceleration comes into picture. So cooperation among the 4 of them is very, very important when you get into the circular trajectory, right. That is why we have picked up the 8 trajectory to show what is the effect of this. On top of this trajectory, if you have an obstacle present, think about some obstacle static, some obstacle is moving, then they need to figure it out whether they can move up to clear the obstacle. If a static obstacle, they can move on the yaw, right. They need to estimate the obstacle, and they need to estimate the velocity of the obstacle. Based on the velocity of the obstacle, all 4 drones have to execute the mission. So that is where the cooperation and prediction comes into picture, right. We talked about recurrent neural network, how it can be used for trajectory prediction. It plays an important role here, right. Now look at various other problems. One of the interesting problem is confinement escape, right. There is a drone which enter into the region for collecting some information. The objective of the drone, after collecting the information, they have to escape from the boundary before it get caught by other agents. The other agents are marked in the red color, right. The drone which is green knows where is the boundary present. The only information it knows where is the boundary. It does not know how many red drones are there, whether they are going to cooperate or coordinate, it does not have an idea. It has to escape from this region. That is a very interesting problem, right. Now other cases, you have a large forest region. In the large forest region, there are fires, right. You do not know where exactly the fire is, you need to detect them. When you detect, if it is a large fire, if you notice here, one single drone is trying to quench the large fire. This fire size is so big, a single drone will not be able to handle. You need a multiple drones to come together. You can't put distributed UAV here to handle it. It has to be swarm of UAV. Moment if I define a swarm what I meant is a group of UAV flying together, they will be within the circle of radius or swarm radius, but they are free to move in any direction. They move in such a way that they do not go out of the communication radius. When you have swarm of UAV, then the large fires could be mitigated. If you have a distributed swarm of such UAV flying around, we can handle multiple growing fires, right. There are a lot of problems are there. Perimeter defense. The inverse of confinement escape is the perimeter defense problem. All the red ones are just operating in the perimeter, and the invader comes from outside. I need to detect and hold them back, right. Again, swarm of UAVs are needed for this. Large area border surveillance, search and rescue mission, right. When there is a natural calamity, you need to detect the survivor and rescue. or deliver certain package to the surveyor. You don't know where they are. You have rough idea potentially where they could be, but the exact location is unknown. You need to detect and deliver a package or rescue them, right. Those kind of applications also required swarm of UAV. Target tracking and monitoring, convoy to be protected. These are some of the typical problems where adverse missions take place in an adverse environment. Okay, let us try to understand why swarm of UAV, right. As I mentioned earlier, group of UAV flying together, right, in a circle of radius r. They are free to fly in any heading, but they will maintain that all of them are stay in one specific radius r. Okay. They do not go outside the radius. If they go outside the radius, they change their heading such that they could be within the swarm. Okay. Now that swarm has an advantage. It has a collective intelligence. Each UAV has its own sensors, right. Together they can get lot of information about the environment which is unknown, uncertain. They are resilient, right. Even one fails, still they can continue the mission. They have a multiple perceptions, so that more information from a different view can be collected, right. They are connected, right. So that is another advantage, connected, so they can have a resilient characteristics and they can just share the information through the network and take the information, collective information to make a decision, right. Now what this swarm is doing, it is looking at an adverse environment which is changing dynamically, right. The changes are not static, they are dynamic. For example, forest fire, the fire is not going to stay at one point, it is going to keep spreading, right, keep increasing its size based on the wind direction as well as carbon content, moisture, where the moisture is less, it will start spreading in that direction, right. Those are unknown, right. So you could have a situation where flood is there, flash flood. You do not know how the flood is going to move, how it is going to, which are the areas is going to pass through, right. It is an unknown, uncertain environment where it is keeping observation. Based on the observation, they are going to act on it in the adverse environment, right. It could be a search and rescue mission. But the observation, right, what are the observations they are getting? They are trying to get the target, right. They are trying to localize the target, they are trying to get the map of the region so that the other UAV can come together. They are trying to track the target such that there could be some action you can perform, right. Now what are the problems associated with swarm solutions, right. Let us look at one by one. Sensor, partial observability, right. Your sensor is not able to see everything. From let us say two UAVs are flying and there is a wall between, one UAV sees the target, the other UAV is also nearby, but the wall is blocking the visibility of the target, right. Partial observability becomes biggest challenge because I can't see, but how do you expect me to act on it? That is a challenge. I may have multiple sensors, right. I can have electro-optical, I can have IR, I can have a radar, I can have a LiDAR. Which sensor to be used? When to use? See, if detecting fire, the best way to detect, first look for a smoke, then you find the local region, then look at the heat gradient, then you can approach, because just looking at camera alone is not sufficient because smoke will cover the entire region. It is not sufficient to see, right. Which sensor to use? How do you schedule the sensor to get to the target is a challenge. Why? Because we don't know the target. We don't know the target nature to be precise. Based on the type or location, it will be different. The target could be heterogeneous in nature, means heterogeneity could be in terms of speed at which it is moving, right, or direction at which it could move. It could be a highly agile target, right, and what kind of resources are required to detect this target is also unknown. State uncertainty, right. You have sensor, you are measuring the state. Simple problem we talked about, GPS is not there. Then how do you estimate your position information, right? That is also going to factor in cooperation. Now moving from sensor, the second important aspect going to be your computational uncertainty, right. You could have a problem which is spatial and temporal. You have a problem which could be, some task could be handled by single robot, some task could be handled by multiple robot. It could be simultaneously you may have to act. For example, forest fire fighting, the drones need to spray liquid, right, or chemical to quench the fire. Sometimes they have to act sequential. You need to deliver one after another in a specific sequence, right. What is that particular nature of the target which is unknown for me? I have a limited computational resource. I can't run a complex algorithms, right. I have to use my computational resource very efficiently. Not only computational resource, every target requires certain action to be performed. To perform that action, I have a resource on board that is also limited. I have to use that resource effectively. The challenge comes in scalability and reliability, right. This is domain dependent. A domain, it has to be domain independent. I can't say okay, this algorithm should be just applicable only for this particular problem. Domain generalization is the biggest issue, right. On top of it, no free lunch theorem comes into picture. No algorithm works for all conditions. Even though you have a camera, different algorithm detect target with a different probability. Which one to use? When do we use? That will also add an uncertainty in your computation, right. The biggest challenge is consensus on cooperation. I see a target, you also see a target, who will go and act on it, right. That cooperation is also required, which requires a computation again. The other challenge is communication. Communication range is limited. Data to communicate is also, the bandwidth is also limited. Shall I send the entire sensing information to him, or shall I send my decision information, or in between the hyperspace to him? What do I share? The connectivity link should be there, no, to communicate. The link may be uncertain sometime. Execution challenges comes into picture. You have to make decisions in dynamic, right. It is not going to be fixed space. The decision space is also a challenging, and sometimes they have to get into formation control. For example, forest firefighting happens, they have to fly in formation. How do we get that formation accurate with the uncertainty being communication as well as uncertain environment? Actuation mechanism may be an issue, right. So these are some uncertainties pose an important challenge in swarm technology. Now, to make decisions, people use decentralized approach because it is scalable, right. So I can use a decentralized decision making strategy. I can't guarantee optimality, but at least locally optimal it is more than sufficient. I can use market driven, stochastic approaches, or I can use a team theoretic approach. Means when two of UAV seeing the target, they try to maximize the team benefit rather than their own benefit. They work as a team, right. So, you can use a team theoretic approach, or you can use a game theoretic approach for consensus, or you can use learning based solutions, reinforcement learning, spiking neural network, or online decentralized learning, or distributed AI solutions. Any of this could be applied, right. But challenges for all these are the sensor uncertainty, the decision challenges we talked about earlier, the communication uncertainties are going to affect the performance of these approaches, right. Now, let us take one simple problem. Okay. Try to understand how we allocate the resources for a problem which has multiple tasks to be performed by every drone to defend the perimeter. Okay. Let us say this is my perimeter where my critical resources are present, and I want to protect this particular perimeter. This is my territory, right. I want to protect this particular territory. I do not want anybody to come in. The protection of a critical infrastructure is what we meant territory here. I want to protect that. I do not want anybody to fly over so that they do not get the information about this particular region. It could be your airport, or it could be your army installation, or it could be your oil refineries or factories. Some safety critical infrastructure is what we are looking at. The area is defined by you. I do not want any intruder within this area, right. What is my intruder? It is a freely moving UAV, can move into the territory to collect information about the critical infrastructure. That is my intruder. Whoever enters the black line is my intruder, right. So, the red one is an intruder, he collects the information, right. So, what I do to prevent this, I need to have a defender. The green UAVs are the defender. There are multiple UAVs. These UAVs operate on the perimeter of the territory, the black line, right. They operate in the perimeter. They need to identify which drone is an intruder and where he could intrude. Based on the position and time of arrival into the perimeter, he has to reach that particular location and capture him. I assume that there is a capture mechanism is there and he is able to capture, right. So, he has to neutralize it. The defender reaches that particular location when the intruder comes in and capture. You can ask question why perimeter is a single line. A perimeter need not be a single line, it is a small region, right. I am representing as a black line, it could be a region of let us say 100 meters, right. I want to capture anyone within the 100 meters region. I do not want anybody to enter that black line. If they enter that black line, the game is over, right. So, I do not want anybody to enter, right. What is my objective? I want to capture the intruder before they enter the territory. Now, there are some challenges here. Scalability, right. Can I handle the large territory without modifying the architecture, right. The dynamics of the intruders, the number of intruders changes with respect to time, right. How many intruders are there is going to change with respect to time, because nobody knows how many are going to come in. And what is the strategy of approaching? The maneuverability state of the UAV is also going to be affected, right. I do not know how maneuverable they are. Are they just going to fly in a straight line? I have no idea, right. I have to have a mechanism, a distributed sensing mechanism, right. Each UAV has its own sensors and they can see certain regions only. The other UAV can see other regions only, right. If I have one more UAV, the two green UAV, they know together they can see multiple intruders who are coming in, right. The limited sensor range of the defender also affects the performance significantly. That leads to partial observable problem which I was mentioning earlier, right. Now, to handle a large territory, right, I should not modify the architecture, whether this small territory or a larger territory, the algorithm architecture should remain same, right. The intruder changes with respect to time, the maneuverability status of the UAV, the distributed sensing and sequential capturability, which means one defender can capture multiple intruders in a sequence. They can't capture them simultaneously, they can capture them sequentially. That's an problem we are looking at, right. Let us say I capture one, by the time I capture the other one, it could enter. Let us say two UAVs are approaching the territory, two intruders approaching the territory simultaneously, but I have only one defender, I cannot capture both, right. In such cases you need to have a dynamic defenders. When I sense such kind of things, I should be able to send more defenders to my perimeter, right. If I have one more defender, I can send him to capture, but I do not need all the defenders in my territory all the time, which means I will be wasting my resources, right. I want a minimum number of defenders in my territory so that they can sense the entire environment and provide information to me. If I see two of them approaching simultaneously, I should be able to send a reserve defender to handle that kind of a coalition among the intruders to enter the territory, right. So then there is a challenge. How many reserve defenders should we keep? We have no idea about how many intruders are going to come, right. How many reserve defenders? From where we should I send? Shall I keep the reserve defender in the center or shall I keep it in some location? Where is that location? How many I will keep in those locations? These are the bigger challenges for handling protection problems, right. Now let us try to formulate this problem in a mathematical sense. We make certain assumptions, right. So one by one you have to relax, those things you can do it when you get into swarm based courses, right. I am just giving you a flavor and I am talking about the challenges here, right. The moment I detect an intruder, right. So here if you see I have about m intruders, I3 is flying away from my territory, hence I3 is not my intruder, whereas rest of them are flying towards my territory, they are all called intruders. I am assuming that these intruders are going to fly straight, they are not intelligent, okay. We can relax one by one, they are not intelligent, which means once I detect the initial position and heading, I can predict they will be reaching this particular location at time t. But I do not know their velocity, okay. I need to sense their velocity. Once I sense the velocity, I can find out time of arrival, right, estimated time when this intruders will be reaching the territory. Then the task here is to capture all of them, right, that becomes a spatial and temporal. When intruder 1, right, reach the position P1 at T1, that is T1. There are m tasks, the number of tasks is unknown, right, the task location and time is predicted, right. How many tasks are going to be there? It is unknown at any given time, right, and the task changes with respect to time. Now if I am representing the task in a time versus angle, I am assuming this origin to be represented at the center of the territory, and then if I am trying to represent as a plus or minus pi and the time, and this is how the tasks are arranged in a spatial and temporal fashion. Now I need to find out the region. Within that region I am going to go one on one. If any intruders are within that region, I will give a priority to those intruders, right. I will continue to track him till I capture or he moves away from the priority zone. So, I need to define the zone within the region. If there is an intruder, that intruder will be assigned one defender on a priority basis. The defender will be continue to track this intruder till the intruder moves away from the priority region or captured. Okay. So, we make some assumptions. The velocity max of the defender is always greater than the velocity of the intruder. That is when you will be able to move, right. So, where to keep the reserve stations, right. The reserve stations should be kept in such a way that there is a minimum distance they could reach the regions very effectively. It is a region dependent problem, right. So, we have to optimize to find out where to keep. If there is territory shape changes, the location will change, right. Then I need to monitor. Which region I should monitor? Definitely I need to monitor the priority region, right. Minimum I need to monitor that. Beyond a priority region, I need to monitor certain distance to make sure anybody enters in that particular region, I will start tracking, right. That is the thing we are talking of. We are talking about safety again. What is my safety distance I want to monitor, right. So, omega m, it depends on a gamma and beta. Beta is a safety factor, and I try to optimize this to find out what is my region going to be. Once I identify the region, I need to find out how many number of defenders I should use, right. I want all the points in the region should be monitored continuously. I know each defender has a camera or some sensor. The sensor has a specific radius, right. How many defenders I should keep in such that all these points which is marked in the red is always monitored by the defenders. If it is done, then I can say 2 defender is sufficient. If not, I need 3, I need 4. I have to optimize this also to find how minimum number of defenders I should keep in my territory such that I can monitor my regions effectively at all time, right. Then comes the problem. We have task, right. We need to minimize the energy consumed by the drones, right, and each drone can be assigned to one task, right. They can have multiple tasks, but one task at a time. The same task cannot be assigned to 2 different drones, right. Almost one task just immediately after the current task, and almost one task, and each task is executed by only one. So, we have to put some constraints and which wanted to minimize, and we optimize this problem, and we define the cost. What is the cost for a first task? What is the cost for subsequent task? And we have to compute this, and then that is why I said the onboard resource, computational resource will solve this problem and say, okay, these are my first tasks, these are my subsequent tasks, which means this is my trajectory. Now, I need to have a conflict resolution algorithm. I can say this is my trajectory. What about the other? What will be his trajectory? And if both of them are going to the same task, we have to resolve who has the minimum cost, and that he will take that particular task, which means he has to re-optimize his problem leaving that particular task, right. And that need to be shared, and consensus need to be created so that they know their decision. All these should happen very fast, right, and that should be computationally light also, right. So, they will solve this particular problem to resolve. Once some task is infeasible, they will just assign a large value so that they do not get that particular task, right. What is infeasible means? I see a target approaching a location, and I cannot reach that location within that time, then that task is infeasible for me, right. So, we need to understand which are the tasks infeasible, then you have to assign a cost which is very large, task which has happened earlier, right, time before the current time, all infeasible tasks. This is all completed tasks we are not interested in. Like this we formulate the problem and we run. I am trying to give you an understanding, right. There is a territory, I pick the reserve locations based on the optimization, and this is my region of priority, and this is my region of sensing. Then I try to see how many points are there in the sensing region and try to identify the sensing radius and trying to assign. You see the defenders are on the territory. Based on the infeasible task, new defender comes into picture. The new defender after assign, right, you see the new defenders are added. Once the task is over, I do not really need for sensing purpose, I will go back to my research station, I will not stay there, right. So, that is how the dynamically they capture, the dynamically they move out such that they provide a coverage, right. When you are performing a task, there could be a possibility that you may not cover a sensing region. In such cases also you deploy a new defender just to cover the region such that you can continue to monitor. So, D4 has been launched to just to provide the coverage, right. Task is not only to neutralize, task is also to provide coverage. Once the coverage is taken care, it will move back, right. So, now the one of the problem here is, I can show how we can perform with respect to what is the agility of the defender. If the defender becomes highly agile, then it will be very difficult for us to handle it, right. So, how agile we can handle, right, how smart they are. Moment you have they are highly agile, then you need to have more defenders to really capture, right. So, those kind of analysis need to be done. Okay. There are challenges that one need to understand when we talk about the problem of territory defined. See, we make an assumption these drones are going to appear and move in a straight line, not necessarily they move in a straight line. Number 2, you may not have a sensor to detect due to fog or smoke in that region, then it will be very difficult, right. You may be able to detect them only in the priority region, then what will you do, right. So, there are lots of challenges are available. Those are interesting problems. Those who are pursuing this course want to do a project, they can take up some of these problems and trying to solve, okay, that will help you to understand better. Okay. Thank you.